Hello friends, for Aerospace Propulsion ISA Activity 2, me and Viresh have chosen the topic of electrothermal propulsion. In this PowerPoint, we will see what is electrothermal thrusters and their types. So let's get started. So before moving to the electrothermal propulsion, let us understand what is plasma propulsion. So basically, plasma propulsion is a propulsion technology in which the propellant, that is fuel, is ionized or it is bring into plasma state. Here, the temperature of the propellant is increased to a point that it become ionized. Hence, it is known as plasma propulsion. Here, we can say the temperature of the propellant may be at the nearly 5000 Kelvin or more. So, electrothermal thrusters are a type of plasma propulsion system. So, let us introduce to the electrothermal thrusters. So, definition: electrothermal thrusters use electrical power to heat the propellants. So, basically, we can say it is a heater type of device which heats the propellant. So, function: hot gases that is fuel or propellant expanded in a convergent divergent nozzle for thrust production. So, what is the importance of this? The key technology, it is a key technology in a spacecraft propulsion system. In space, we can use these electrothermal thrusters for better utilization of the small amount of thrust. So next note, the propellant can be heated by using either electrical resistive power or by electrical arc discharge. And based upon this, there are two types of the electrothermal thrusters. They are resistor jet and arc jet. So in this part, I am going to explain about the resistor jet. And the next part, which is the arc jet, will be conducted by my fellow mate, that is Viresh. So let us move toward the what are the type of electrothermal thrusters. They are a resistor jet and arc jet. Here is a brief introduction towards what are those. So in resistor jets, these are electrical resistance is the main key element which is used for heating the propellant. But in case of arc jet, electrical arc discharge method is used. So in resistor jet, propellant heating via electricity heated surface. Here surfaces are heated. But in arc jet, propellant flow through a electrically arc discharge. So let's move resistor jets. So propellant gas is heated by making it in contact with electrically heated solid surface. So there are four types of this resistor jet, or we can say these are divided into the four categories. First one is the straight coiled wire. So the propellant passing along the heating element which restrict the heating rate of the propellant. So we can understand by simply an example of let us take one bottle. So here and consider there is one funnel here and you are heating it with the help of a candle or anything and you are pouring water from the top of the funnel. So what will happen because of the speed of water and the rate of burning of the candle or the element which are you using for the heating, the water will not be heated properly. So in this you have to rapid heat the water, but it is not happening. So it is not as much as effective as the other things. So the straight coil wire is less effective and has very less efficiency. So to overcome this, there are made some advancement. That is, the coils are placed in transverse way. So that type of resistor jet are called transverse coiled wire, transverse coiled wire resistor jets. So to improve the heating rate of the propellant, heating coils can be placed in transverse direction of the flow. So in this image, sorry. So in this image, you can see the heating coils are placed into the transverse direction. So because of this, the heating of the propellant can be done in very good way. So next is the sphere bed method or sphere bed resistor jets. Here, a bed of tungsten sphere is used to heat the propellant by passing current through the contact resistance of sphere. However, it enhances the bulkiness with incurring significant pressure loss. So in this type of resistor there is a pressure loss. Next is the chamber wall resistor. The heating chamber can be used as a resistance to heat the incoming propellant while overflow. So next, so here you can see the detailed diagram. This is the straight coiled wire. Here is the transverse, is a bed you can see, and here is a chamber. So next, regenerative resistogens. So what is this concept? So because of this, here you can see, as we discussed the four types of the resistor, there are some also heat losses occur due to the wall. As the wall from the wall, many energy, electrically heated energy will be passed. So to avoid it, there are some insulations. So let us understand what are these. The performance of such kind of resistor jets depends on the extent of heat transfer from a resistance element to the propellant gas stream and radiative heat transfer from the complete assembly, as heat losses through the wall is basically loss of power in the thruster. As I said, heat loss is the loss of power in the thruster. So next, in order to reduce the radiative heat transfer, the radiative shields are provided around the active tungsten heat element, which not only reduce the heat losses but also transfers the heat, the incoming propellant and in reentrant gas flow. So here what happens, this not only reduces the heat losses, but it also helps to again reheat the fuel. So the propellant is, we can say, two times heated. Once with using our technology, that is what we are say the resistance, and then another with the help of the walls, we can again heat this propellant, which will be far more efficient. So thus it is called regenerative resistor. As multi-chamber heat exchanger is used to recover heat losses through the chamber wall. So in this diagram, you can see next propellant in electrothermal thruster. So commonly here hydrogen and ammonia and nitrogen are used as the propellants. And next the performance, hydrogen offer highest due to lower molecular mass. As the mass of the hydrogen is lower, so it can give a more best performance, we can say. Heating compression, higher temperatures achieved in arc jets. Next, specific impulse and efficiency. So here specific impulse increases with the gas temperature. As the gas temperature increases, that is, as we heated the propellant, the specific impulse of the our jet is increased. Then efficiency and reliability decrease with higher temperature. Here efficiency and reliability decreases with the higher temperatures. Then heating losses higher in arc heating due to ionization and dissociation. So next, higher chamber pressure effect. So while higher pressure improves the heat exchange and reduce the dissociation losses, it also leads to increased heat transfer rate, accelerated nozzle throat erosion, higher stress on the chamber walls. Next, chamber pressure consideration. The chamber pressure is electrothermal thrusters is chosen based on various factors. They may be propellant type, propellant dissociation and recombination characteristics, heat exchanging performances, and rate of nozzle throat erosion. So uses in space we can say the space applications of these resistor jets are, despite having a lower thrust and mass flow rate, electrothermal thrusters are preferred for space application due to their compactness. As we can see, they generate less amount of thrust, and also their size is very less as compared to the other engines. So we can use them in the satellites and many things in the space application, where very less thrust is needed for the directional and other stability purposes and movements. So next is high reliability and low thrust requirements. So as I said, low thrust requirement, so we can use them into the space applications. Next application, they are especially used in satellite operation, satellite keeping, station keeping, drag neutralization, altitude control. Example, a register jet like Satcom 1R and G Star 3 and Meteor 31 are employed in various space applications due to their high performance levels. Next, engineering challenges. The primary challenges in designing a register jet involve creating and maintaining conduits and insulator that withstand the higher temperature while maintaining the electrical integrity and vacuum seal. So it is very important that our coil should be able to withstand the electrical load we are applying or electrical charge we are applying. It should not be melted. So next is material selection. The tungsten and boron nitride are effective as high temperature conductors and insulators. They are both high temperature conductors and insulators, so they can provide us better amount of heat energy. Use of metals. Refractory metals like tungsten, tantalum, molybdenum, rhenium, platinum, and their alloys are employed for the resistance element due to their ability to withstand high temperature. Next is the temperature limitation. So currently resistor jets are limited by the temperature tolerance available in material. Future prospect. Advancement in high temperature materials could overcome the current temperature limitations of resistor jets. So we can say if materials are improved, so we can use, there will be some advancement into the resistor jet as the metal will not be melted.
Thank you, Omkar. And from here on, I'll continue. And just now we saw about the resistor jets. So now let's move ahead towards the second part of the like electrothermal thrusters. It is arc jet thrusters. Uh, we'll see about how the components of arc jets, its operational principle, challenges, and the research and developments about this electrothermal thrusters. So, arc-jet thrusters are a class of electric propulsion system that convert electrical energy into thermal energy through the production of an arc. This involves accelerating high temperature, high pressure gases to supersonic speeds in a nozzle, similar to a chemical rocket. The anode and cathode, typically made of a tungsten for its high temperature tolerance, play a crucial role in initiating and sustaining the arc. The CD nozzle, power supply, and propellant feed systems complete the ensemble. So let us see the operation of arc jet thrusters. The operation of arc jet thrusters involves maintaining a steady DC voltage across the anode and cathode. To initiate the arc, a higher voltage is applied initially, ensuring the breakdown of cold gas. Automatic start is triggered by the gas flow into the arc discharge chamber. Paston law dictates the breakdown voltage depending upon the product of arc gap and gas pressure. In space conditions, a low product value aids spontaneous arc discharge. Challenges include temperature distribution, thermodynamic imbalance, arc generated radio noises, and ionized wake. However, these challenges are met with innovative solutions to ensure the stable and efficient operation. So, key points and challenges. Uh, Propellant introduction is crucial with propellant feed near the cathode to keep the anode cooler. The working fluid heats up significantly when passing through the arc, and ideally, the arc attaches in the divergent portion of the nozzle. However, high current arcs can be unstable, leading to arc instability and electrode erosion. Mitigating strategies involve external magnetic fields and swirling propellant flow. The chemical arc jet thrusters (CAJT) introduces catalytic decomposition of hydrazine, enhancing the specific impulse and utilizing hydrazine's liquid state for space storage. Now, what are the propellant choices according to their efficiency? Various propellants like hydrogen, helium, argon, neon, nitrogen, ammonia, and N2H4 are used, with hydrogen being preferred for its heat transfer properties. Despite being less efficient compared to electrothermal thrusters, arc jet achieve higher propellant temperatures and exhaust velocities, leading to enhanced specific impulse. The thrust to power ratio is significantly higher than the resistojets in arc jets. So the chemical arc jet thruster combines monopropellant like hydrazine with arc jet, releasing the additional chemical energy. The augmented electrothermal hydrazine thruster enhances hydrazine dissociation through electrical and resistive heating, utilizing conduction and convection for heat transfer. Now, let's turn our attention to the dynamic world of research and development in electrothermal propulsion technology. Scientists and engineers are actively engaged in addressing challenges and pushing the boundaries of this fascinating field. Here are some key areas that highlight the cutting edge advancements. First up, we have the exploration of advanced materials. The goal here is to develop materials with higher melting points and improved thermal conductivity, extending the operational life of thrusters, enabling them to function at higher temperatures. This involves the research into refractory metals, ceramics, and composite materials, all aimed at enhancing the durability and performance of our arc jet thrusters. Now let's talk about the intriguing concept of magnetic nozzles. Instead of relying on traditional physical nozzles exposed to high temperatures, researchers are exploring the possibility of using magnetic fields to shape the direct of the flow of plasma. This could potentially reduce erosion and improve thermal management, marking a significant leap forward in thruster design. Our third area of focus is microwave heating. Imagine using microwaves to heat the propellant. This isn't your kitchen microwave but a novel approach to achieve more efficient and uniform heating. The aim is to increase overall efficiency, providing higher specific impulse and reducing erosion compared to traditional heating methods. Next in line are Hall effect thrusters. By employing a magnetic field to confine plasma, these thrusters seek to address one of the challenges faced by traditional arc jets, that is electrode erosion. The magnetic field traps and accelerates the charged particles in a controlled manner, promising improved efficiency and longevity. Now let's explore the concept of pulse arc jets. Imagine modulating the arc current to improve thrust control and reduce erosion. This technique holds the potential to extend the operational life of our thrusters. It is a bit like pulsing the engine of a car to optimize fuel efficiency, but in the vast expanse of space. Speaking of the real world applications, NASA is actively developing a 10 kilowatt class arc jet thrusters for deep space missions, and the project is aimed at creating a reliable and high performance propulsion system suitable for demanding requirements of deep space exploration. Meanwhile, the European Space Agency is investing in the development of 50 kilowatt class Hall effect thruster for Smart 1 lunar mission. This project leverages magnetic fields to improve efficiency and reduce wear, making it a promising technology for future lunar and deep space missions. These ongoing projects showcase the commitment of space agencies and researchers to advancing electrothermal propulsion technologies. The goal is clear: enhancing efficiency, reliability, and versatility in propulsion systems, ultimately paving the way for the future space exploration and travel. So, as we look to the stars, we are also looking forward to the innovation that will take us there. Thank you.